हेलो 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 ठीक। Good afternoon to everyone. Once again, post lunch session. अभी जो है 10-15 मिनट्स बात कर सकते हैं, स्टूडेंट्स के लिए है. वी विल मेक दिस सेशन इंटरेक्टिव सेशन बेसिकली. अभी कितने स्टूडेंट्स हैं वैसे यहाँ मैं बात कर सकता हूँ? कितने स्टूडेंट्स हैं? ओके. तो अ, अभी जो थोड़ा डिस्कशन हुआ था वो मैंने ये कोशिश किया था उसमें कुछ रिसर्च से रिलेटेड चीजें आपको को कुछ उसमें पूछना समझ में आया है या थोड़ा बहुत आगे सकता है काम? आप डिस्कस कर सकते हैं उसमें अगर किसी को कुछ डिस्कस करना, क्योंकि ये मानना है उस तो एंशिएंट टाइम में जो मैथमेटिक्स है अभी मैथमेटिक्स है उस थोड़ा गैप बेसिकली. तो वक्त का कॉन्फ्रेंस का इस तरह की जो कॉन्फ्रेंसेज हैं जो स्पेशली उसमें एक्सपर्ट डिलीवर करेंगे उसका पर्पज ये है कि इस चीज को फोकस करते हुए उस गैप को फुलफिल किया जाए किसी भी तरह से, चाहे तो एंशिएंट टू मॉडर्न और मॉडर्न टू एंशिएंट किसी भी तरह से. तो एक ट्राई था अटेम्प्ट था उसको चूज करने का कि कैसे जो एंशिएंट मैथमेटिक्स में अब मॉडर्न मैथमेटिक्स को रिलेट किया जा सकता है. जैसे एक एग्जाम्पल था ग्राफ थ्योरी का, स्टोका की टर्म में था, उस पर वर्क किया जा सकता है उसको करेक्टराइज करने के लिए. क्योंकि एग्जिस्टेंस आप देख चुके हैं, अगर किसी भी चीज का एग्जिस्टेंस है तो हम आगे सोच सकते हैं उसको कैरेक्टराइजेशन की डायरेक्शन में या आगे मूव कैसे करेंगे इस डायरेक्शन में सोचा जा सकता है इजीली. अगर हम थोड़ा सा इफ यू पुट सम एफर्ट and if we have the knowledge of some ancient literature. आचार्य पिंगला का बहुत बड़ा कंट्रीब्यूशन है बाइनरी नंबर सिस्टम में. जनरली हमें यही पता है, जैसे मैं बता चुका हूँ टॉक में, वो लिबनिज इसके फादर थे एंशिएंट मैथमेटिक्स को नंबर सिस्टम को देने वाले. यही तो पढ़ते हैं ना हम लोग. या अगर इलेक्ट्रॉनिक्स है तो वो उनको पता है, वो डिमोरिस ने या जॉर्ज बुले ने उसको एनालाइज किया, ये हम बोलते हैं. ठीक है. तो अभी अगर किसी को इससे रिलेटेड कोई किसी स्टूडेंट को कुछ डाउट्स है या डिस्कशन है या कोई क्वेश्चन है तो जो प्लेटफॉर्म है वो ओपन है. अभी हम लोग डिस्कस कर सकते हैं क्योंकि डिस्कशन से बहुत सारी चीजें निकल के आती हैं. जो यंगस्टर्स हैं, जो रिसर्च स्कॉलर्स हैं, तो दे आर वन हु कैन लीड and produce the very good quality kind of work they can produce. Anybody अगर है तो आप बात कर सकते हैं. अभी लास्ट में कोई है? अच्छा, ग्राफ थ्योरी का किसको आइडिया है अभी? यहाँ तो पढ़ाया जाता है, सीसीएस में तो पढ़ाते हैं, सिलेबस में है, एमएससी मास्टर्स में है. मतलब ग्राफ थ्योरी क्या है ना, वो ये है कि उसके अंदर एक दैट इज द ऑर्डर्ड पेयर्स ऑफ वर्टिसेस एंड एजेस. यहाँ तक ग्राफिकल रिप्रेजेंटेशन नहीं है कोई भी, ओनली दो एलिमेंट्स है, वर्टिसेस एंड एजेस, वी एंड ई. ठीक है. पर ग्राफिकली वी कैन एक्सप्रेस, वी कैन रिप्रेजेंट ग्राफिकली इफ वी जो एलिमेंट्स हैं सेट वी के, इफ वी टेक एज ए वर्टेक्स, फाइन, ऐसी एज को लें तो उसको हम लिंक, दो वर्टेक्स को ज्वाइन करने के जो काम जो हम ज्वाइन करते हैं वो लिंक या एज कहलाता है बेसिकली. ये दो ही कंसेप्ट याद रखिएगा आप, जिसको नहीं पता. वर्टेक्स एंड कनेक्टिविटी. कनेक्टिविटी कब होगा? अगर कोई ना कोई रिलेशन होगा. ठीक है, रिलेशन होगा तब उसको हम कनेक्ट कर सकते हैं, रिलेशन में बी लेस देन, ग्रेटर देन, ब्रदर, सिस्टम, इवन if no connection, no relation, that is also one kind of graph. That graph is called null graph of empty graph. That is also concept in the literature. Fine. तो आपको देखना है एंशिएंट सिस्टम में, वहीं से स्टार्ट करने का मैं इसलिए जोर दे रहा हूं क्योंकि अभी जो एंशिएंट नॉलेज सिस्टम है, जो इंडियन नॉलेज सिस्टम है, उसमें लॉट ऑफ अपॉर्चुनिटी है इफ वी स्टार्ट। अगर हम स्टार्ट करेंगे उस वर्क को करने के लिए, जो एंशिएंट सिस्टम को पढ़ेंगे, देखेंगे, श्लोकों को देखेंगे, तो क्या होगा उससे जो हमारे जो फोनर्स हैं, जो आउटसाइडर कंट्री हैं, ठीक है, अगर आप कुछ अच्छा रिजल्ट देंगे तो दे विल अट्रैक्ट टुवर्ड्स आवर सिस्टम। अगर वो अट्रैक्ट होंगे तो अपने लिटरेचर को देखेंगे। अब लिटरेचर को देखेंगे तो अगर संस्कृत हो या किसी भी लैंग्वेज में, इंडियन लैंग्वेज में हो, तो दे विल ट्राई टू हायर और ट्राई टू हेल्प अवर, और दे विल मूव अवर कंट्री अगेन। अभी हाँ, जब वो मूव करेंगे तो क्या होगा, फिर अपना जो नॉलेज है भारतीय ज्ञान परंपरा का, तो हम उसमें फैक्ट देंगे, प्रूफ देंगे, तो एवरीवन विल एक्सेप्ट विद द प्रूफ। प्रूफ इज नेसेसरी, इज मैंडेटरी। जैसे ग्राफ थ्योरी का एक कंसेप्ट मैंने बताया, 7036 में बोलते हैं, आइलर की बात करते हैं। लेकिन जो ग्राफ थ्योरी कंसेप्ट है, अगर हम बात करें एंशिएंट टाइम की या उसके पहले भी, हमें पता था एक स्केलेटन है। बहुत एग्जाम्पल सिंपल है, भगवान राम के जो वंशज हैं या उनके पहले भी रहे होंगे, मुझे नहीं पता इतना, लेकिन अगर वहीं से माने तो आगे के बहुत सारे उनकी पीढ़ियां भी हैं, पहले की भी आगे की भी हैं, असेंडेंट डिसेंडेंट दोनों तरह के हैं, ठीक है। तो दैट मींस एक स्केलेटन जो एक है, रफ डायग्राम तो एग्जिस्ट करता है ना, वहाँ पेरेंट्स हैं, चाइल्ड हैं, उनके भी चाइल्ड हैं, फिर ग्रैंड चाइल्ड हैं, ऐसे करके एग्जिस्ट करता है। हो सकता है वहाँ नाम नहीं दिया हो, उन्होंने ग्राफ नहीं किया हो, आइलैंड ने उसको डिफाइन किया है कि ये ऑर्डर्ड पेयर है, इसको हम ग्राफ बोलेंगे, लेकिन ऑलरेडी था ना एग्जिस्टेंस। तो एक प्रूफ है। अगर हम ये बोलते हैं कि रामायण एग्जिस्ट करती है, उनके एंसेस्टर एग्जिस्ट करते हैं, तो हमारे पास में ये कहीं दिया है, ये लिखा है, किसी भी उसमें देखेंगे जो लिटरेचर में आपको मिलेगा। एग्जैक्टली नंबर मुझे नहीं पता, मैंने नहीं पढ़ा उसको, लेकिन इट इज गिवन, ये मैंने देखा है उसको, ठीक है। जब उसको कोड करेंगे तो उनको बिलीव कराना है कि ये ऑलरेडी हमारा लिटरेचर में एग्जिस्ट करता है। तो वो कैसे, हम ये बोल सकते हैं, उन्होंने उसको मैथमेटिकल डिफाइन करा। वो कैसे एग्जिस्ट में आया, उन्होंने एक कोनिग्सबर्ग ब्रिज प्रॉब्लम थी जो कि रशियन में थी, उन्होंने उसको ग्राफिकली एक्सप्रेस करा। एक्सप्रेस तो हमने भी कर रखा है उसको, उनको उसको बता दिया कि ग्राफ थ्योरी का वहां से ओरिजिनेशन हुआ है, लेकिन इसके बारे में हम लोग ना तो पढ़ाया जाता, ना हम उसके बारे में सोचते। जो पहले से था हम उसको क्यों नहीं बताएं कि ऑलरेडी एग्जिस्ट करता है ट्री की फॉर्म में, है कि नहीं। तो ये चीज है। अब हम लोग तो प्रकृति का भी इतना सम्मान करते हैं, उसकी पूजा करते हैं, ठीक है। वृक्ष ऑलरेडी कंसेप्ट है, ऑलरेडी डिफाइन है, तरु वृक्ष ये सब चीजें मिलेंगी आपको। अगर है तो उसमें ये भी है, उसमें रूट का कंसेप्ट भी है ना, ब्रांचेस का कंसेप्ट भी है, लीफ का कंसेप्ट भी है, गिवन है उसमें, लेकिन कोई इसके बारे में बात ही नहीं करता। बेस बनाने के लिए, जब बेस बनेगा तो एजम्पशन बनेगी। बेस कहां से बनेगा, किसी एविडेंस से बनेगा। एविडेंस कहां से बनेगा, तो दिस इज अ वन काइंड ऑफ एविडेंस, हमारे पास में प्रूफ है इसका। तो वहां से स्टार्ट करिए, आप उसको आर्गू भी कर सकते हैं अगर फैक्ट के साथ में हम बात करेंगे तो ये एक वे है। तो ऐसे हम उसको देखेंगे। एक एग्जाम्पल मिला है हमें एग्जिस्टेंस का, उस एग्जिस्टेंस के उसको बेस मानते हुए, या बेस मत मानो, एग्जिस्टेंस एक मान लीजिए, आप अदर स्लोक को ट्राई करना फाइंड करने का, और उसमें देखना अगर मैं उसको ऐसे रिप्रेजेंट करूं या ऐसे में क्या पैटर्न डिजाइन करूं कि वो एक ग्राफिकल फॉर्म में वो एक्सप्रेस हो जाए। तो हम बता सकते हैं कि उस श्लोक के अंदर वो पर्टिकुलर ग्राफ जो है वो कंटेन करता है या एम्बेडेड है, उसके अंदर ऑलरेडी एम्बेडेड कंसेप्ट है, वो ग्राफ उसके अंदर एग्जिस्ट कर एम्बेडेड है, मतलब निहित करता है उसको, मैं बात करूं तो, ठीक है। तो वो कौन सा ग्राफ है, ठीक है। जब ये कौन सा ग्राफ है तो उसको उस फॉर्म में, एक कंसेप्ट था पैट्रिनेट का, मैंने उसको एक्सप्लेन नहीं किया, आपको नहीं पता होगा, ये मैं बिलीव कर मतलब अज्यूम कर रहा हूँ, जनरली नहीं पता होगा, लेकिन वो डायरेक्टेड बायपैटल ग्राफ है। तो उसमें जो डायनामिक्स मिलेंगी, जो इसकी इंटरमीडिएट स्टेट्स मिलेंगी, तो हम उसको उसके कॉर्नर पॉइंट्स पे, वर्टिसेस पे रिप्रेजेंट कर सकते हैं, जिसको हम वहां बोलते हैं रीचेबिलिटी ट्री। एक दिन मैं उसको एक्सप्लेन कर दूंगा ओनली पैट्रिनेट को, कंसेप्ट को, तो वहां उसको देख सकते हैं। ये इसलिए डिस्कशन हो रहा है क्योंकि एक उनको लिंक करने में एक बहुत बड़ा रोल प्ले करेगा, पहले के सिस्टम को और एग्जिस्टिंग सिस्टम को। अदरवाइज और भी सिस्टम्स होंगे, वो आपको देखने पड़ेंगे, जैसे ये एग्जाम्पल है, ऐसे और कौन से सिस्टम्स हैं ये हमें देखना पड़ेगा, फाइंड करना पड़ेगा, अगर हमें इस सिस्टम को, ज्ञान परंपरा को आगे बढ़ाना है, तो ऐसे हमें सोचना ही पड़ेगा। नहीं सोचेंगे तो अगेन फिर वो जो चलता आ रहा है वो चलेगा। आप लोग को आंख बंद करके उसको विश्वास करना पड़ेगा और आप उसको करेंगे, कोई नहीं रोक सकता उसको करने से। नेक्स्ट जनरेशन भी यही पड़ेगी, तो राइट टाइम है उसको करने का। क्या कह रहे थे आप? हाँ, आ जाओ इधर आ जाओ। डिस्कशन सेशन बहुत इंपॉर्टेंट होता है। आप लोग क्वेश्चन आने चाहिए, अगर क्वेश्चन भी डेवलप करना, क्वेश्चन भी फ्रेम करना, इटसेल्फ ए पार्ट ऑफ द रिसर्च। अगर यहाँ पीएचडी स्कॉलर्स हैं, आपकी पीएचडी में अगर आपने 10 to 15 प्रॉब्लम भी आपने फॉर्म कर ली, फॉर्मुलेट कर ली, तो एज ए सेपरेट बुक चैप्टर जा सकता है, ये भी आपको पता होना चाहिए। पूरा चैप्टर, अगर 10 प्रॉब्लम है एक चैप्टर में रखो।
जैसे आपने बताया था गुरु और लघु के बारे में, तो गुरु लघु को हमने कन्वर्ट किया था बाइनरी ऑपरेशन में। जैसे गुरु को हमने 1 से रिप्रेजेंट किया था और लघु को 0 से रिप्रेजेंट किया था। तो उसके साथ में आपने बताया था कि दीर्घ लघु वगैरह जैसे ए आ ई, ये गुरु वगैरह जो काफी हद तक, हाँ, उच्चारण जो हो रहा है वो लंबे तरीके से हो रहा है। तो ऐसे हम क्या पूरी जो हमारी वर्णमाला है उसे हम जो आचार्य पिंगले ने अपनी एक अलग थ्योरी बनाई थी उसका ही पार्ट है, तो उसको पूरी को ही लिख सकते हैं? अभी तो आपने केवल 8 वोवेल्स वगैरह बताए थे, वो आगे तक कर सकते हैं। तो जो पूरे श्लोकास हैं हमारे या पूरी जितनी भी बुक्स हैं, तो हम वो आचार्य पिंगले की थ्योरी के अनुसार मतलब चेंज कर सकते हैं। लॉन्ग स्वर, तो इसमें व्यंजन भी आएंगे फिर? ओके, लघु वाला जो रहेगा। हम्म,
श्लोका को हम उसमें अगर एक्सप्रेस कर सकते हैं तो एक बहुत बड़ा रिपोजिटरी बन जाएगा अपना, ये है कि नहीं, एक्सप्रेस करने का। अब वो एक्सप्रेस करने से बहुत सारी चीजें सोल्व हो जाएंगी, जो है बहुत डिफिकल्ट होंगे रीड करने में, उनको इजी हो जाएगा। कुछ मैकेनिज्म भी बन जाएगा रीड करने का कि कहाँ से स्टार्ट करें। हो सकता है कुछ ऐसे श्लोक होंगे जिसमें कुछ कॉमन होगा, पाथ कॉमन होगा, कुछ में डिफरेंट होगा, कि मान लो यहाँ से यहाँ कॉमन है तो सबका कॉमन चलेगा, उसके बाद में डिफरेंट होगा। तो ऐसे कितने ऑप्टिमल वेज हो सकते हैं, आप ऐसे सोचिए ना बाद में कि वो एक से ज्यादा श्लोक पढ़े जाएं या एक श्लोक पढ़ा जाए उसमें, ये पॉसिबिलिटी है ना उसमें। ऑप्टिमल क्या होगा, अगर टाइम बचे, आपका टाइम सेव हो, आपका जो कंप्यूटेशनली गुड हो रहे आपका, ठीक है ना। जब ये ऑप्टिमल सीक्वेंस आपको मिलेगी तो आप तब आप सोच सकते हैं उसकी एल्गोरिथम को डेवलप करने के लिए। अब जब एल्गोरिथम बनेगी तो डेफिनेटली एनहांसमेंट होगा ना टेक्नोलॉजी में, फिर उसको इंटरप्रेट करिए आप जहां भी कर सकते हैं। बाइनरी नंबर सिस्टम में अगर हम बात करें वो यही तो होता है, जो स्टोर होती है इंफॉर्मेशन वो 0-1 की फॉर्म में स्टोर होती है। अब 0-1 फॉर्म में उसको कैसे ऑप्टिमल बनाए, जो ऑलरेडी एग्जिस्ट है उसको मोर और ज्यादा ऑप्टिमल उसको बनाया जा सकता है, ठीक है ना। तो उसको सोचना पड़ेगा कैसे बनाए। अब 2^64 का चेस का एक एग्जाम्पल है, ऐसे आपने भी सुना होगा। क्या इतना अभी हम कैपेबल है 2^64 का जो जो बिट है, जो नंबर मिलेगा उसको स्टोर करने में? मेरी नॉलेज के अकॉर्डिंग तो नहीं है। 264 वेरी हाई, वेरी वेरी लार्ज नंबर, नॉट एबल टू एक्सप्रेस, है कि नहीं। तो ऐसे कितना हो सकता है, क्या आप रिड्यूस कर सकते हो? ऐसा कौन सा नंबर है जिसको हम कर सकते हैं इसके द्वारा? ऐसा क्या ऑप्टिमल नंबर होगा पावर का? वो क्या बोले, 32 बोले, 12 बोले, 10 बोले, जो ऑलरेडी है। तो उससे देखो एल्गोरिथम को इंप्रूव करो तो आपको नेक्स्ट मिलेगा, उसका इंप्रूवमेंट मिलेगा। एक बार की इंप्रूवमेंट किसी ने भी डेवलप कर दिया ना, तो पूरा का पूरा जो यूनिवर्स देखेगा फिर हमें, अगर हमने ऐसा कुछ कर लिया तो। एल्गोरिथम बहुत इंपॉर्टेंट रोल प्ले करती है, एक छोटी सी एल्गोरिथम से ही, और उसमें वैदिक मैथमेटिक्स के जो टेक्निक्स हैं, जो ट्रिक्स हैं, वो बहुत हेल्पफुल है लॉजिक को डिजाइन करने में। जो एल्गोरिथम के जो लॉजिक्स हैं उसको सोचना पड़ेगा, क्योंकि उससे शॉर्टकट ट्रिक्स निकल के आती हैं। जब शॉर्टकट ट्रिक्स हैं तो उनको इन जो एल्गोरिथम्स ऐसे बनते हैं, जो पैटर्न बनते हैं, उनको मिनिमाइज करने में, ऑप्टिमाइज करने में वो बहुत इंपॉर्टेंट रोल प्ले करते हैं। फॉर्मूले नहीं है तो बनाओ, और भी फॉर्मूले बनाओ। सोचो, इंडियन नॉलेज सिस्टम ही जाना चाहिए, ये हमारा एम्फेसिस होना चाहिए, है ना।
सुबह कितने बजे चले वहां से, दिल्ली से?
May I request to all the online participants who are interested to ask any question from the sir, they can ask. Online participants also ask any question.
Sir, good afternoon. This is Radhika.
Any query?
Attending your session online.
We are checking the chat box, so they can send any kind of query. They can write your query in the chat box. देखो क्वेश्चन क्या है। Okay, Radhika ji, have you raised your hand? It is by mistaken, or are you?
No. Yes, I've raised the hand. Yeah.
Okay.
Hello.
Hello.
Yeah.
Radhika,
thank you, sir. Thanks a lot for the very interesting session.
thank you.
I just have one small query.
जी.
Right. So I work in the area of fluid mechanics. So could you please suggest some Sanskrit base for this fluid mechanics, which I can go through and then learn something from our own literature and then do the work?
Literature for the fluid dynamics, sir?
Yes, sir. It's fluid dynamics.
Fluid dynamics.
Yes, exactly, sir.
Iska I don't know literature, but
yes, something related to our from our Sanskrit literature, like something related to this one, so that because it was so inspiring. Your lecture was so inspiring. I thought I should.
That's okay, but I've not worked about on this kind of literature, but I'm still trying to find some Vedas. I don't have copy of Vedas, but
Okay, sir.
that finding comes from my research. Whenever I've thought about some formula and some Pingla mathematics, Pingla number system.
Yes, sir. Yes.
Coming from that time, whenever I'm working in my, discussing with my student in my department, but
yes,
maybe some literature will be available. I do not know right now, but if I get the right appropriate reference, I will also consult Dr. Anil and Sivraj sir is here and Kailash sir. Then we will share you if during that.
Thanks a lot, sir.
Yes.
Thanks a lot, sir.
Yes.
Thank you so much.
Any other queries from online participants? Raise your hand, or you can write your query in the chat box.
And one more things to my dear participants. Actually, unfortunately, right now we don't have any sufficient repository or and the literature that we need to still to develop a kind of good repository. That is also right now we demanded and required. We don't have, unfortunately. Even all work done by the Pingla and Palini, even we don't have the all work done by him. That is also problem with us, because in our system a lot of ups and downs are there. So many races, due to some races, arrival of some races in our country. So maybe that is due to some our knowledge system has been, that's why so many things are happen till ancient to till now. So this is due to that reason we don't have organized way literature, but we have. we should try to develop and find such kind of repository into one single platform like this. Bas, madam. Thank you, sir. Thank you very much. For,
thank you so much, sir.
Giving me the opportunity, sir. Thank you, sir. Thank you, and thank you, madam.
Sir, thank you, sir.
And
thank you so much.
audience, and we will meet you somewhere, some other. Okay, I will leave now, and thank you very much again. Thank you.
Thank you so much, sir. गजेंद्र सर ने आज जो लेक्चर दिया वो पिंगला सिस्टम, नंबर सिस्टम के ऊपर था, और सर ने बहुत ही अच्छे से समराइज किया उसमें बाइनरी नंबर सिस्टम, मतलब बहुत कुछ सर ने ऐसा जोड़ा हुआ था जिसमें ग्राफ थ्योरी भी आती है, तो आपको पता चलता है कि वैदिक गणित किस किस फील्ड में काम कर सकता है। तो सबसे अच्छी बात यह है कि आप जो वैदिक गणित के नए आयाम मीन्स न्यू डायमेंशंस के बारे में अगर हम बात करें तो वो भी हमें इससे जानकारी मिलती है। जितने भी लेक्चर्स आप इस वर्कशॉप में देखेंगे वो हर एक आपको नए नए फील्ड में मिलेंगे, और उसी से हमें पता चलता है कि कितने फील्ड्स हैं जिसमें आप रिसर्च के लिए भी आगे आ सकते हैं। सो थैंक यू सर। गजेंद्र सर, आज आपने बहुत अच्छा लेक्चर दिया हमारे साथ, आप फिजिकल मोड में प्रेजेंट रहे यहाँ पर। और नाउ आई वेलकम फॉर द नेक्स्ट सेशन स्पीकर, ही इज जेम्स क्लोवर। आई थिंक he has connected with us online. James, you can open your video. If are you here? James, can you hear us? Yes.
Hello. Hello. Yes, I am here, but the host needs to allow me to show my video.
Thank you, James. Before we start, I just introduce your brief introduction actually for the participants and all the dignitaries which are connected with us. So James has researched and taught Vedic mathematics for over 40 years and has led international teacher training programs, public courses and lectures on the subject in the UK, USA, India and the Philippines. He is the academic director for the Iwvm. Iwvm stands for International Advancement of Vedic Mathematics and has national co-led 14 international conferences. He has written 5 books and edited 6 conferences proceedings, as well as the publications of the numerous papers and articles promoting the Vedic mathematics systems. He has a long experience of curriculum design for mathematics in all over schools and colleges also. His work in Vedic mathematics is inspired by simple questions such as what is number, what is zero, what is shape, what do the sutras really means Vedic sutras. There are 16 sutras, how they can apply. So I would like to introduce James himself. Actually, he is the co-founder and chairman of Iwvm, and he is presently now will present his presentation here on the Vedic mathematics. So please welcome James. Over to you.
Thank you, Sanaya. Can you hear me?
We can't see your video. Can you share your video?
Yes, just a moment. Can you hear me?
Yes.
Good.
Can't see your video.
Yes, all right.
Yeah.
In fact, I will be showing 2.
Nice to meet you, James.
Thank you. Thank you. I will be showing 2. The first is on the synergy of Vedic mathematics, synergy in Vedic mathematics to do with arithmetic and algebra. Can you see my screen?
Yes, of course.
Okay. And the second is to I take one particular sutra, Untitled, and show some of the applications of it, which reveals the flexibility of the sutras. But we'll start with this one. In Vedic mathematics of Tirthaji, the arithmetic algorithms relate to algebraic principles, or an algebraic technique is applied and transposes into an arithmetic method. In respect of teaching and learning, or pedagogy, many students fail to see the connection between algebra and arithmetic. However, Vedic mathematics brings out and highlights this connection, resulting in a deeper understanding of any particular topic. In terms of aesthetics, the synergy between arithmetic and algebra exposes a more unified and satisfying approach. This paper illustrates some of the connections between the numerical and algebraic methods. I'll just clarify a few terms here. We need to understand what is an equation, an identity, a formula, and an expression. Here are 4 statements. Can you identify them? I hope so. Well, the first on the left is an identity. The first on the right is just an expression with no equal sign. The bottom left is a formula. It's an equation with a practical application. And down on the right bottom is an equation with one solution. So an equation is a fundamental statement containing an equality in which there is a definite solution or group of solutions. Equality in mathematics is fundamental and, in fact, is described by one of the sutras, Shunyam Samya Samuchchaye. When the totals are the same, there is 0. How this relates to equality is tautological. Where the 2 sides of an equation are equal, there is no difference. So the 0, the shunyam here, means no difference. And we know what expressions and formulae are. An identity is a statement of equality that is true for all values of the variable. For example, 4x plus 2x plus 7x is 13x is an identity because it is true for all values of x and is therefore true for any particular value of x. It is universal in the sense that it is true for all values and is particular because it's true for any particular value. Now, when high school students learn coordinate geometry of straight lines and curves, misunderstanding this issue is a common barrier to success and understanding. The equation of a line is universal to all points on the line, and any particular point on the line satisfies the equation. The sutra involved with identities and equations is Vyashti Samashti, particular and general. So we have a universal statement like 4x plus 2x plus 7x is 13x, and then we can take particular examples of this. And the particular statement is like a reflection or shadow of the universal. Tirthaji's first example of relating algebra and arithmetic comes from his proof of Nicolam. Having described how to multiply 9 by 7, 9 into 7, by using complements 1 and 3, as a proof, he then lays down the algebraic principle, x minus a into x minus b, x squared minus ax minus bx plus ab. Factorizing the first 3 terms gives x into x minus a minus b plus ab. With the substitution, and this is the key, substitution of 10 for x, this becomes 10 minus 1 into 10 minus 3, 10 times 10 minus 1 minus 3 plus 1 times 3. In other words, 63. The substitution of x is 10. Is a key element of the synergy between arithmetic and algebra. For example, using vertically and crosswise to multiply 21 by 31, giving 651, this can immediately be transposed into multiplying 2 binomials, as 2x plus 1 times 3x plus 1 is, working from the left, 6x squared plus 5x plus 1. And these 2 statements are pretty much the same. This can be extended to multiplying polynomials of any degree in one line of working. So here we have 342 by 236, which if working from the left, using vertically and crosswise gives 6, 17, 34, 30, and 12. And similarly, the algebraic version of this is multiplying two quadratics. Using exactly the same coefficients, we see 6x to the power of 4 plus 17x cubed plus 34x squared plus 30x plus 12. These two procedures are reflections of each other. Of course, the arithmetic answer appears different when the carried digits are dealt with. Furthermore, there is another link between the arithmetic and algebra when multiplying, and this is an application of the Gunita Samuchchaya Gunita Sutra, product sum, sum product. The full wording in context is the product of the sum of the coefficients in the factors equals the sum of the coefficients in the product. I'll just go through an example of this. So I've written here the statement, the product of the sum of the coefficients in the factors equals the sum of the coefficients in the product. So example, 2x plus 3 multiplied by 5x plus 7, giving 10x squared plus 29x plus 21. The sum of the two factors are 2x plus 3 and 5x plus 7. The sum of the coefficients in the factors are 2 plus 3, 5, and 5 add 7, 12. And the product of those is 60. And the sum of the coefficients in the product is 10 add 29 plus 21 makes 60. This is always true for multiplying polynomials and can be utilized for dividing polynomials as well, and factorizing. The same works in arithmetic, but due to carried digits, we must work with digital roots. Here is the same example, but in arithmetic, 23 times 57, giving 1311. The digital root of 23 is 2 plus 3, 5. The digital root of 57 is 5 add 7 is 12, and 1 add 2 makes 3. Multiplying these two digital roots is 15. 5 times 3, 15. And the digital root of 15 is 6. Then when we look at the answer, 1311, the digital root is also 6. This will always work. In this context, the sutra reads, the product of the digital roots of the factors equals the digital root of the product. The algebraic version is useful for many problems involving products and factors, whilst the arithmetic version is useful for checking answers in multiplication and division, and can also be applied to addition and subtraction. However, it's not a foolproof check because, for example, if I wrote the answer instead of 1311, I wrote 1131 and get the digits muddled up, it would still pass the test. So it's not foolproof. Now, for those of you who are mathematicians, you will know that when you see a long number, a string of digits, and you have to copy it down, sometimes you will move digits around in that number because of a subconscious desire to find pattern. And mathematicians are prone to finding patterns. It's quite fun. Squaring. The method of straight squaring of numbers uses duplex. Using duplexes is derived from the algebraic pattern of coefficients. So if we square a quadratic binomial like ax plus b all squared, getting a squared x squared plus 2abx plus b squared. With x is 10, this becomes 100a squared plus 2abx plus times 10 plus b squared. For example, 32 squared, the a is 3 and the b is 2. So a squared is 9, 2ab is 12, and b squared is 4. Extending this to a trinomial squared, you can see the pattern of coefficients becomes a squared, then 2ab, then 2ac plus b squared, then 2bc, and then c squared. And these are the duplexes for 3-digit number. Let's have a look at an example. Well, this goes through the duplex process. For a single digit, the duplex is just its square, like 4. The duplex of 4 is 16. For a 2-digit number, it's double the product. So the duplex of 37 is 3 times 7 doubled, which is 42. For a 3-digit number, the duplex is the product of the first and last digits plus the square of the middle. So for 327, it's 3 sevens doubled plus 4, which gives 46. For a 4-digit number, the duplex is double the product of the first and last digits plus double the product of the middle 2. And with an example like 2, 3, 4, 5, we get 2 5s doubled plus 3 4s doubled. Example 345 squared. The working can be done either from the left or the right. We set down the duplexes for 3, 3, 4, 3, 4, 5, 4, 5, and 5. And of course, we arrive at the correct answer of 119,025. And if you understand vertically and crosswise multiplication, then this is all very obvious. Cubing 2-digit numbers. Tirutaji lays down this method where he takes a 2-digit number like 24 and shows us how to cube it. And the process is to take the first digit of 24, namely 2, and write down its cube, which is 8. And then using the ratio of the digits, 2 to 4, which is the same as 1 to 2, apply that ratio to set down a geometric sequence consisting of 4 terms. So we're doubling, starting with 8, arriving at 16, then 32, and then 64. What will happen, as you will see later in a minute, is that the last term will always be the cube of the second digit, namely 4 cubed is 64. The second step is to double the middle 2 numbers. 16 becomes 32 and 32 is 64. And then lastly, to add up, taking care of place value. So starting from the right, 4 is set down with 6 to carry. Then 32 add 64 add 6 is 102, which is 2 with 10 to carry. 16 add 32 add 10 is 58, which is 8 with 5 to carry. And then 8 add the 5 makes 13, giving the answer. It's a nice method. But how does it work? To discover how it works, we need to look at the algebra. So if the 2 digits are a and b, we have a plus b cubed. And so setting down, setting down the first term a cubed, now the ratio is b divided by a. In the same way that the ratio with 24 is 4 divided by 2, here we've got b divided by a. So multiplying the a cubed by b over a, we get the second term, and then multiply that by b over a gives the third term, and again multiply by b over a to get the fourth term. Simplify gives a cubed, a squared b, ab squared, and b cubed. Double the middle 2 terms, 2a squared b and 2ab squared, and then add up to get the answer a cubed plus 3a squared b plus 3ab squared plus b cubed. And of course, you will recognize this as the standard expansion of a plus b cubed. So this method, and he doesn't point this out, he just describes the method. This method of cubing 2-digit numbers is in fact actually just a simple application of binomial expansions for cubes. Yeah. In Tirch's seminal book, the first topic in which he explicitly shows the transition from algebra to arithmetic and vice versa is Parawarcha division. 27 divided by 12 can illustrate how the method works. So he transposes the 2 of 12 and then divides the first digit of the dividend by the first digit of the divisor. 2 divided by 1 is 2. That becomes the first quotient digit. 2 multiplied by bar 2, bar here means minus, is bar 4, and then that's set down into the next column and add up the remainder. When you think about it, that's 7 add minus 4 is 7 take away 4, 3. That's all that's necessary. If you realize that 2 12s are 24, then to get the remainder, all you're doing is subtracting that 4 from 7. His first example, however, is algebraic, and it's this 12x squared minus 8x minus 32 divided by x minus 2. Here he transposes the negative 2 to 2 and starts with 12x squared divided by x is 12x. 12x multiplied by 2 is 24x, which is written in the second column. Add up and divide by x, giving 16. 16 times 2 is 32. And then this is added up for the remainder. His first arithmetic example is 1, 2, 3, 4 divided by 1, 1, 2. And it's a similar process, but working with 2 transposed digits rather than just 1. And he goes on to further larger divisors, both algebraic and numerical. The simplest divisor for Parawarcha division is 11, as shown in the next example, where because of the the first digit of the divisor is 1, you don't have to do any dividing, and because the transposed digit is -1, we just land up doing subtractions. And so the quotient becomes 2, and then 5 minus 2 is 3, 7 minus 3, 4, 4 minus 4, 0. And we can compare this with the algebraic version, which would be x plus 1 divided into 2x cubed plus 5x squared plus 7x plus 4. And here you can see that the two methods are identical. The same algorithm is also used for developing power series in which the powers of x are ascending rather than descending. So here we can look at 1 over x, 1 minus x. And so the divisor is 1 minus x. The dividend is 1 plus 0x plus 0x squared and so on. The minus x of 1 minus x is transposed to plus x. And the result is the well-known series 1 plus x squared plus x cubed, etc. Now, going back to the substitutions, having a look at this, if we let x be 0.1 and have a look at this fraction, 1 over 1 minus x becomes 1 over 0.9 if we let x equal to 0.1. Multiplying top and bottom by 10 gives 10 over 9, which is 1 and 1/9, or 1.1 recurring. And if that same substitution is put into the power series, 1 plus x squared and so on, we get the same thing. 1 plus 1 over 10 plus 1 over 100 and so on gives 1.1 recurring. Later on, Tirta describes the method of flag division, which is exactly the same as Parawarcha division, but does away with the transposition and so uses subtraction. I'm sure this is familiar, where the 2 of 32 in this case becomes the flag digit, the Dwajanka. And subtractions are used, it's very, very similar. It's almost identical to Parawarcha division. In fact, one reason why straight flag division is called the crowning gem is because the algorithm involves forms the basis of division by vertically and crosswise, square roots, Paravarcha division, Nicolam division, recurring decimals. And correlated, of course, will be Nicolam multiplication and multiplication by vertically and crosswise and factorization. So that particular algorithm gives a great link, a linkage to all sorts of other areas. It appears that many of the arithmetic algorithms in Vedic maths come from or are certainly related to algebraic algorithms. This connection helps bring together algebra and arithmetic and assists in understanding the algorithms themselves. Ultimately, these relationships are expressed by the sutra Vyashti Samashti. Thank you.
Thank you, James.
Are there any questions?
And thank you so much. So James has concluded digital roots, duplex, and cubing any two-digit numbers, and some division methods like flag method. It is called in Hindi Dhajank Vidhi. So ये बहुत ही easy method माना जाता है. अगर हम वैदिक गणित से करें तो इसका जो method है ध्वजांक, उससे आप किसी भी डिवीजन को बहुत आसानी से कर सकते हैं. So he has explained the Dhajank method here. So any other queries about this session from online participants or offline participants also? James, you would like to say about Vedic mathematics or about India or about CCS University like that?
Oh, well, there's a lot to say about Vedic mathematics. I'm not sure where to start though.
Yes, means we would like to introduce means what is Vedic mathematics. First of all, हमें यही बताना होगा. Means we have to introduce Vedic mathematics to all the participants here. So I would request that brief introduction of Vedic mathematics is required here.
Okay, so as you know, there are 16 sutras and a similar number of subsutras in Vedic mathematics, as formulated by Shankaracharya Sri Bharati Krishna Tirtha around about 100 years ago. He spent years studying at in Sringeri Mup in South India, near Bangalore, and formulated these from his studies of Veda and from his influence in Advaita philosophy. And the book of Vedic mathematics was published after he passed. It was published in 1965, and since then there's been quite a lot of research. People in my country have been involved in research in Vedic mathematics since that time. And what it does is each sutra has many different applications. The second video I'm going to show takes one sutra and shows a whole variety of applications. And what the sutras do express the way the mind naturally thinks. So the mind is not a random place, but when it solves a problem, it uses a variety or a limited number of channels in which to solve any problem. And each sutra has expresses one of these channels and has very many applications because it's they're quite fundamental. At this, a limited number of channels or ways of thinking is a little like the analogy I use often is that of playing a musical instrument. Like when you learn a musical instrument like the piano, for example, there are a limited small number of notes in the octave. The octave has 7 notes. And then it's got some sharps and flats as well. So on a piano keyboard, you have white notes, and then the black notes are for sharps and flats. You've got 12 notes in an octave. After that, those notes are repeated to the higher octave or lower octave. So you've got these notes, a very small number of notes. But when you ask yourself this question, how many pieces of music is it possible to compose from this small number of notes? Well, of course, it's infinite variety. In the same way, the sutras apply to so many, each one applies to so many different types of problems, and also they can combine up with each other. Then some of them also support other ones. So it's a very flexible system. So that's one aspect. The second major aspect is that given any single problem, can I continue?
Sorry about that. You can continue, James.
Okay. The second major aspect is that given any single problem in mathematics, there are a variety of ways in which it can be dealt with. I mean, just to take a very simple example, if you consider how to take the number 56 and add 29, you might start by adding the tens and then add the ones and then do a carry digit, or you might start with the ones and then add the tens, or you might say, well, I'll add 20 and then add 10 and then subtract 1, or I'll add 30 and subtract 1. You could just, there's a great flexibility in the way you can do very simple problems. Anyway, the fact of the matter is, when we get to Vedic maths, that there are usually a large number of ways in which any particular problem can be solved. And each one of those ways has a different sutra. I mean, a very simple case, like 98 multiplied by 92, you can use Nicolam multiplication, or you can use vertically and crosswise multiplication. So on the one hand, you've got each sutra has many applications, and on the other hand, each problem has a number of sutras that can be used to solve it. So you get this intertwining. The sutras are very flexible. Now, important to understand this is that often when people first come across Vedic mathematics, they think, oh, here are some mathematical tricks. It's not like that. When you see a mathematical trick, it's like magic, sure. But that's not maths. Maths is when you understand it, not when it's just a trick. If it's just a trick, a magic trick, then what that means is you don't understand how it works. When you do understand how it works, then it becomes mathematics. So now, Vedic maths does provide a number of alternative, what we would call alternative or unconventional techniques. But it's not just that, because it covers conventional techniques as well. So it's really a different approach to mathematics. one part of Vedic maths is that it does have these techniques and methods that are fast and easy and so on, but that's only one part. It covers, you will find that the sutras work whenever you are performing mathematics. And it's more that the sutras describe what is happening in your mind moment by moment by moment. So you have to look at what is happening, and so it's a more personal type of approach. It's a more humanistic, a more human approach to mathematics. Now, about the flexibility, what I'd like to do is show the video for where I take one sutra and describe various applications of it. It's about 25 minutes long. So I'll just try and see how to do that. Where did I put it? It's in MP4. Here we go. Can you see this? Is this visible? Can you see this? Hello? I'll just play it. So this presentation is about a little known sutra.
Hello, James. Can you hear me?
Yes, hello?
Okay, okay. Yeah, we can see your video.
You can, good. Can you hear it?
Yeah. Can continue.
Okay. Which goes by the name of Untitled. And this is made of two words, Untitled and Ewa. The word Ewa usually means only or indeed. And the word Untitled, the case ending is the yu on the end, as dual case ending. The word Antya usually means final, but can also mean the limit or the edge of something. And I will be showing, I think, 10 or 11 applications of this sutra. Generally translated as only the last terms. But this word Antya does have several meanings. And look at some of those. It can mean the limits of something, the edges, the outermost parts, the first and last digits or terms, the last two digits, the last terms, or the first terms. So it has all these variable meanings. And any problem in maths that comes under this sutra can be solved using one of these meanings. So the first application I'm going to look at is in arithmetic series. So we'll start with this. The mean value of an arithmetic series is half the sum of the first and the last. So let's look at this example. The series consisting of 6 terms, 5, 9, and so on through to 25. And we can find the mean by adding the first and the last and dividing by 2. So x bar is 5 plus 25 divided by 2.
वहाँ जाना था सर ने मना कर दिया क्या बोल नहीं जाना
And 6 times 15 is 90. You can understand this from the conventional formula. So this says that the number of terms times the mean will be n over 2 times a plus l. where A is the first term and L is the last term. And the formula for the last term is A plus N minus 1B. And so you can see how this relates to the conventional formula N over 2 times 2A plus N minus 1B. The next application is for geometric series. And this can be the well-known formula for the sum of a geometric series involves Untitled, and this can be seen in the formula's derivation. So if you have a look at the standard derivation of this formula, we start with a geometric series or sequence A plus AR squared up to AR to the power of N minus 1. On multiplying both sides of this equation by the ratio R, we arrive at AR plus AR squared, etc., all the way through to AR to the power of N. So that sequence has the last term and the following term. So we're going to be looking at those two terms. On subtracting the two equations, we get a telescopic effect where all the middle terms eliminate each other. And we have Sn minus R. Sn is A minus R to the power of N. And on factorizing the left-hand side and rearranging, we arrive at the conventional formula for the sum of terms in a geometric sequence. So for example, in finding the sum of this geometric sequence, 3, 6, 12, 24, we can put in the first term in the formula as 3, and then the next term on from 24 will be 3 times 2 to the power of 4, and that gives 48. So we have 3 minus 48 over minus 1, which gives 45. The third application is very simple, indivisibility. Simple divisibility for 2, 5, and 10 rely on the last digits of a number. And likewise, divisibility by 4 uses the last 2 digits, 8 the last 3 digits, and so on. I won't dwell on that because it's too well known. Here's an application, estimation. Estimation frequently requires rounding numbers to one significant figure, and hence using only the first terms. So for example, we might have this division here, and we want to get an estimate for it. By rounding both these numbers to one significant figure, we arrive at 600,000 divided by 30,000, which is 20. The real value is 18 point something. But for an estimation, this is close enough. And related to this is are the problems involving bounds or accuracy, and these involve upper and lower bounds and require the use of limits. Here's a problem as an example. A rectangle has an area of 15 square meters and length of 3 meters. Both measurements are correct to the nearest whole number. What is the maximum width of the rectangle? So we can write down that the area is sandwiched in between 14.5 and 15.5 square meters. And the length is sandwiched in between 2.5 and 3.5 meters. And the formula to obtain the width is to divide the area by the length. And if we want to find the maximum width, then we have to choose the right values out of those 4. And to get the largest number, we're going to use the maximum area divided by the minimum length, like so. So it's going to be 15.5 divided by 2.5,
which is 6.2 meters. Next application is factorization. There are many cases of factorizing polynomials where inspection of first and last terms proves useful. Suppose we have to factorize this quadratic. One way is to form a matrix of 4 numbers. And in the first column shown here, we put down the factors of 3, namely 1 and 3. This is particularly useful when easy when one of the terms, either the first term or the last term is prime. So given that we've got an easy factor, a relatively easy factorization here, we can use 3 and 1. Then we've got to put down in the second column factors of 14, 2 factors of 14. Well, we could choose 1 and 14 or 2 and 7. And in this case, it's going to be 2 and 7. We've got to get them the right way round. And the way to do this is to look at the sum of the cross product. So here I've put the 2 in the top row and the 7 in the bottom row, because 1 times 7 add 2 times 3, that's the sum of the cross product, gives the middle term, middle coefficient 13. And from there we can just write down the 2 factors as 1x plus 2 and 3x plus 7. Limits of quadratic functions, the 7th application. When completing the square for a quadratic, the last term of the binomial and the last term of the expression provide the location of the minimum or maximum point. So we have a look at this example. Y is x squared minus 6x plus 16. We can complete the square by adding and subtracting 9. And the first 3 terms, namely x squared minus 6x plus 9, gives the square of x minus 3. So we land up with x minus 3 squared plus 7. The minimum value for y is 7, and the location is 3, 7. So we take the minus 3 in the last term of the binomial is minus 3, change the sign to give plus 3, and that gives us the x coordinate of the minimum value. Now, the reason for this is that the minimum value of x minus 3 squared is 0 because it's squared. If x minus 3 was negative, then squaring it would become positive. So once we've got the completing the square, we can obtain the minimum point, in this case minimum, just by looking at the last term of the binomial and the last term of the expression. Application 8, area under a curve. Here we also use limits, of course, in definite integration. So an example, find the area under the curve, y is square root x, between the limits of x is 4 and x is 9. So we form up the integral, integrate to give 2/3 x to the power of 3 over 2, and evaluate between the 2 limits 9 and 4, which gives a result of 38 over 3. Application 9, the method of differences. This gets a bit more technical here. So in this problem is to show that the sum from r is 1 up to n of 1 over r times r plus 1 is equal to n over n plus 1. Let's just have a look at the arithmetic here. If we were to write down the sequence of terms, the series here would be 1 over 1 times 2. That's when r is 1. When r is 2, we get 1 over 2 times 3. When r is 3, we have 1 over 3 times 4, and so on. Now, if we just have 4 terms in the sequence, we get this series here. And what the formula says is that that will be equal to n over n plus 1. And if n is 4, then the result is 4 over 4 plus 1, namely 4/5. Let's just check that out, see if it's true. Well, if we simplify these fractions, we get a half plus a sixth plus a 12 plus 1 over 20. The lowest common multiple for which is 60. And adding those fractions up, we have 30 plus 10 plus 5 plus 3, which is 48. And 48 over 60 is 4/5. So it works for n is 4. Well, to show it algebraically, the first step is to separate out this fraction 1 over r times r plus 1 using partial fractions. And the result of which is 1 over r minus 1 over r plus 1. So each term can be expressed as that. So we can write down the terms in the series as 1 over 1 minus 1 over 2. The second term is 1 over 2 minus 1 over 3. The third term is 1 over 3 minus 1 over 4, and so on. And the last term is 1 over n minus 1 over n plus 1. And you'll notice here that we have, in this series, we've got minus a half plus a half, minus a third plus a third. So we've got a telescoping situation, and all the middle terms eliminate each other, and we're just left with the first term and the last term, namely 1 minus 1 over n plus 1. And these can be added together to form one fraction, which simplifies to n over n plus 1. So this is the method of differences. Proof by induction. The formula for the sum of a series can often be proven by induction, in which the last two terms are used. Here's a fairly common example. Prove that the sum of numbers r squared from r is 1 up to r is n is 1/6 n times n plus 1 times 2n plus 1. The first step is to show that it's true for r is equal to 1, or n is equal to 1. And if we, so r squared will be 1 squared. And on the right, we would have 1/6 times 1 times 2 times 3. And sure enough, that is equal to 1. 1 squared is 1. So the formula is true for n equals 1. Then we assume it's true for n equals k. So we can write the right-hand side of the formula down with n replaced with a k. And then we're going to add the next term to both sides. So the next term will be k plus 1 squared, which is added to both sides. And then we work on the right-hand side. And this simplifies, once you've done the factorizing. So you can see that k plus 1 can be pulled out as a factor initially. And then we can pull out 1/6. And finally, after a little bit of manipulation, we can see that the expression is the same as the initial expression, but with k replaced with k plus 1. So therefore, if it's true for n is k, then it's also true for n is k plus 1. So here we've used the last term and then added one more term on. Last application, small angle approximations using Taylor series. This application uses Untitled in the sense of the first 1 or 2 terms. So the Taylor series for cos x is 1 minus x squared over 2 plus x to the 4 over 6, and so on. And for small values of x, terms in x to the power of 4 and higher are negligible. And so the approximation is 1 minus x squared over 2. And these small angle approximations for cos theta, sin theta, and tan theta are very commonly used in engineering, engineering, physics, astronomy, and so on. So just to summarize what we've shared, what I've been looking at here, we'll be looking at the application of this sutra to arithmetic series, geometric series, divisibility, estimation, bounds, factorization, limits of quadratic functions, area under a curve, method of differences, proof by induction, small angle approximations. And there are several other applications of this sutra, such as in the mean value theorem. So I won't go into further details of that now. But the question does arise, are there applications outside of mathematics? Because I'm sure there are problems in everyday life where we just pay attention to the edges or the limits of an object and not worry too much about the middle. Here's an nice example to finish with. A well-known paragraph written by a Cambridge student illustrates how the use of recognition of limits is a common psychological activity. Can you read this? It's very interesting that it's readable and understandable, and as he says, the words are recognized from the first and the last letters being in the right place. This doesn't always work, particularly if there are lots of double letters involved, but it's an interesting illustration. So I hope that's those applications on the sutra are interesting for you, and you can see how something in this that you can see how these sutras operate, because they each have very many slightly different applications according to the flexibility of the meanings of the words in the sutra. Thank you.
That's a wonderful presentation, James.
Good.
It's just an application of Untitled, only one sutra of Vedic mathematics. And James has described 11 applications of Untitled Sutra. So if there are any query from your side, online participants and offline participants, then they can ask from James. Regarding the session, if there is any query, then you can ask. Okay, James, I have a query from one participant actually. He wants to know what is the meaning of Vedic. Means Vedic mathematics is another part. Only what is the meaning of Vedic? Can you explain for us?
Yes.
Thank you so much.
Certainly. The Shankaracharya Sri Bharati Krishna Tirtha explains the meaning of the word Veda, near the beginning of his book. And of course, what is normally associated with Vedas are these ancient texts like Rig Veda, Sama Veda, Yajur Veda, Atharva Veda. He also describes Veda as being real knowledge which exists in the present moment. And in fact, if you look at the Sanskrit word Veda, it comes from the dhatu, the seed form, vid, which means to know, or to see, or to perceive. And he describes an intuitive process where you can see the knowledge in the immediate moment. In fact, one of the sutras covers the situation where we look at a problem and you instantaneously see the answer without any workings. This happens sometimes. And the sutra for this is Wilokanam, by observation, by inspection. The word, this Sanskrit root, dhatu, or seed form, vid, also comes into English language, which you will recognize. So the word witness, like when you get a witness in a court case, is someone who has seen or experienced an event, a crime. We have the word video. What is a video? It is something you watch when you tune into Netflix or wherever. And a video is something that is seen. So even in English, we have Sanskrit words derived from Sanskrit. So when Shankaracharya uses the word Veda, he's not just speaking about some ancient texts. He's speaking about knowledge which is here in the heart. And to appreciate Vedic maths, this is why I said earlier on, you have to look at the process which your mind is going through moment by moment in the present moment. Look at what is happening in the mind. And this is where we can begin to understand these Vedic maths sutras. So it's to do with knowledge in the moment. That's the simple answer. Knowledge in the moment.
Okay, got it. So you mean to say Vedic means Veda, and Veda means to know about something.
Yes.
To get the knowledge about something, right?
Yes, but it's got to be true knowledge and not imaginary knowledge.
Okay. Got it. So I think Professor Shivras sir has joined the meeting. So I would like to introduce Professor Shivras sir. Sir, please.
Yes, I have joined.
Thanks.
Am I audible, Sonia?
Yes, sir. Yes, sir.
Yes, we have a words to yesterday also.
Hello, Shivraj.
Hello, how are you, sir?
Yeah, I'm good. Good. I'm glad the connection was here. The connection was good.
Yeah. Today network is good, I think.
Yes.
Tomorrow it was not good.
That's right.
So, Sonia, can I start?
Yes, sir.
Okay. Sir, it's very wonderful to listen about Vedic mathematics from you, and we all feel very much, as the title of your talk was the synergy in Vedic mathematics, in particular arithmetic and algebra. You justified this topic in a great manner, and we all are encouraged to work in this area because you did a lot in these directions, and we have one MOU. I can declare in front of the audience that we have an MOU with Institute for the Advancement of Vedic Mathematics.
Yes.
And James is the chair of that particular. It is based on London. So we have an MOU with your association, and I hope that in future we will have better interactions. We will collaborate research in these directions. And as far as I understand, I found that we need documentation of such type of wonderful knowledge, which are ignored in the country of their origin. So you motivate us in these directions. All the participants are delighted to listen to you. So on behalf of Department of Mathematics, on behalf of my country, I personally thanks a lot to you for delivering such a wonderful talk. And I hope that in future also we have an active association with you and your association. Thanks a lot, James. Thank you very much.
Thank you. I would just like to say that, yes, now and again, there is some expertise in Vedic mathematics, which is outside India. And whatever we can do to help, we will. It's in many respects, it's a bit like cricket, because India are so it's an English game, but India are the ones that teach us how to play it.
That's very much important.
India are the masters of Test cricket. So,
not only Test cricket, but you have such a wonderful mathematics also.
The English team have to learn from the Indian cricket team. Anyway, so yes, we will work together. Yeah,
definitely.
Yeah,
thanks a lot. Thanks a lot
for
being with us. And
thank you, Shivraj sir,
thanks
for giving such a kind, thankful note for James Clover. He is the chair of Iwvm. So now we conclude this session. James, would you like to say anything about anything?
Also, I want to thanks to Dr. Sonia for making such a interactive sessions with James and having such a nice words with you. So thanks a lot, Dr. Sonia, for such a interactive sessions. Thank you.
Just your kind support, sir. I'm working with your guidance, so just your guidance is needed to me. So thank you, sir. So now,
Naya, there's just one last thing I would like to say to everybody whilst they are here.
Yeah.
Of course.
Everybody has to practice Vedic mathematics. You cannot ever appreciate or understand it unless you practice it.
Yes, of course. We have to do more.
Even a professor of mathematics, like Professor Dani or whatever, must practice in order to appreciate and understand anything about Vedic maths.
Yes, of course. Vedic maths, we can say mathematics is based on the practice-based subject it is. So Vedic mathematics is need more and more practice for the perfection. So now we can conclude this session. So James, nice to hear your voice and such a wonderful session we have. So,
thank you.
Okay, now we will join tomorrow for the new session. That is the second day session. So we can leave this session now. Thank you so much. Thank you, all of you.
Thank you, Nidhi ma'am, for your nice comment. Thanks a lot.
Okay, we are leaving for today. Today only. We'll join for tomorrow at 10 a.m. with the next session. And just 1 minute. There is a very important message to you. Actually, first session tomorrow, first session will be with Dr. Vedveer Arya sir. He is the Joint Secretary of DRDO and on the Indian chronology. So that will be the wonderful session for all of us. So must wait and watch for that session and must join. If you can join this in physical mode, then must come in the department. Otherwise, you can join in this online session. So thank you all of you. Thank you, James, for such a wonderful session. Thank you once again. Thank you all of you, all the participants. Thank you.